Hello, and welcome to another video on my channel. And today it's again about TIA Portal. And as promised, I have prepared a task for you. A task that can process 3 different colors into a finished product based on a mixing plant. This is a simulated task. In other words, I have connected hardware, but it is connected to this simulation. Here, by activating different outputs, we can let red color flow into the tank. For example, this is also completely animated, green color, of course, and the blue color. Everything is then mixed into a product, and then with the QM1 valve, it is drained into a separate tank, and that is the actual task. There are a few sensors, a heater, and so on, but I would like to slowly build this task with you so that we can program a step chain or be able to program a step chain in FUB and SCL at the end. To start, I would suggest the following. We program a simple instruction, namely, we control this motor. This is called MM1 according to the equipment designation. When we activate the output, Q0.4, the MM1 becomes active and controls or drives this paddle wheel, which is responsible for the mixing process. And I would like to program this task together with you. It is to be controlled with the start button and the stop button. Start, the motor runs. Stop, the motor stops. And of course saves the function. So, let's take a look at the program. And here we see 2 blocks that actually shouldn't be there. This is the FB with its DB. What all this means should be, currently it shouldn't matter at all. The only thing that counts is that in network 1 in OB1, there is a block that is responsible for communication with the simulation. That's actually all we need to know. I'll also fold that away again. And why am I explaining this? I don't want to mislead you with such things. They are simply there to, as I said, be able to start or carry out this simulation. And that's why we'll just start programming in network 2 instead of in network 1. To avoid any questions or ambiguities, it was important for me to mention that, and we begin with the actual programming. We have said that we have 2 inputs and 1 output that we want to control. And in the Siemens diaportal world, there are various, under simple instructions, under bit linking, blocks that you may or may not know. The typical block is the SR, which is used quite often, and we will pull it over to the shortcut bar. If you click in the middle of the empty window with the left mouse button, and then click on the SR block, or if you simply drag it in, then we have, so to speak, called up the desired SR block in its form in network 2, and can now parameterize it directly. That's the idea. However, we need to consider or discuss a few things. We can select its related blocks in the upper right corner of this block, namely the RS. That means if I made a mistake and a wiring of this block has already occurred, like here an assignment, some inputs, here an output from my side, or a marker, better said, or a virtual memory, or a variable of mine. So now I have really counted everything that exists. When everything is switched, I eventually notice that this block is not the right one, but I would like the SR instead. Then I can quickly swap it like this. The other option would be to delete this block. Then of course all connections would be gone and I would have to rewire everything. That would be quite annoying, and thus one could simplify some things, so to speak. Yes, we have here input, S, R, so set, reset. The SR block is memory retaining. That means if I give a pulse to the set input here, the block retains the state until I reset it. And in the set. In this situation, the Q output delivers a 1, and I could control an output, for example. Very often it is the case that one does not use this function at all, but writes the output directly above it. And the first question is, does that even work? And the second question would be whether that is even correct. I actually answer the question by trying it out. Specifically, I0.0 would be the input for start, and I0.1 would be the input for the stop state, and A0.4 in the simulation before is the output for the mixer. Okay, so far, so good. We need to discuss and consider one small thing in advance. The stop button is, unfortunately, designed as a normally closed contact at this point. So the simulation gives us a normally closed signal when we press the stop button. This means that in the idle state, there is a 0 here. That is not entirely correct. A stop button should always be implemented as a normally open contact. And when we should normally measure a permanent 1 signal here. When it is activated, this signal is interrupted, and then we would also need to place a negation, an inverter, here, so that this input is inverted or flipped. That is indeed a very, very good input, certainly. Indeed. If you want to remove the inverter, please do not try to delete it using the delete key or backspace. But you just need to click here once and then click the same component in the shortcut bar again, and then it will be gone. So now let's get to the actual task, whether this works or not, as I have programmed it here. Let's call that programmed. One small thing is also important. Namely, when I click on the entire folder here, I transfer everything that is in my project. If I only click on the component, I only transfer the change in the component. Makes sense to transfer everything the first time and then see where I currently stand. What have I changed? Is it even worth transferring the entire project again? Or can I just transfer the change? This small thing that I may have changed, is that enough? So this is the button to load the device, so to speak. We click on it and load everything into our PLC. Finishing up. So basically I am done, and I have the option here in the upper area among all the tools to activate this tool or button, because it is an observation mode. I activate this, and lo and behold, I am connected to the PLC and can observe the process through my software. What is happening in my PLC actually only works when everything here, when all the symbols are green. This means they symbolize that my programming device or my PC and my PLC are on the same level. I have the same program on both sides, and only then can I observe it. If I make a change here, then although I am now online, I can immediately see that I have unequal blocks. Specifically, main OB1 is unequal at this point, which is why I can no longer visualize it. I will now remove this assignment again, transferring only the OB1 by clicking here. If I click on transfer, it usually goes faster. So the more complex your program becomes, the longer it takes to transfer the entire project. At this point, as I said, main OB1, a small change, loading, goes relatively quickly, and then I am equal on both sides again. Then I can observe main OB1 without any problems. Okay, then let's call up the visualization or our system again. It looks like this. I will move it a bit to the right so we can control it better. And first, I will activate I0.0. And you can see that the mixer is running. That is the desired function. With the stop button, I can pause everything again. That's exactly how I described or requested it beforehand. That works, and I could now say, okay, everything is correct. What is the next task? And then we could continue. No, we couldn't. It is not quite right. It is actually wrong. And you don't do it this way. In principle, you could program everything in OB1 one after the other and say, okay, I'm done, transfer, it's running, I'm going home. However, you have to consider the following. A PLC is not responsible for such trivial tasks. So just start, stop. I can also use other. Hardware for selection. So the PLC should actually be capable of controlling automatic processes. It can solve much more complex tasks. This is now the simplest thing that can be done, and it is also wrong. Why is it wrong? First of all, it is not correct to place an output over an SR block. There is the output M of the SR block, which is actually the output of an SR block. The SR is actually there to monitor the state. It must also occupy a memory space where it can store its state. In this case, I did not give it any memory space, but said, just store your state in an output. And that is not correct. It works, and it also saves resources. That used to be interesting regarding resource savings. Nowadays, that is no longer an issue. Therefore, one should place a virtual memory here, such as a variable or a fixed address memory, a memory bit, in this position. For now, we will stick with the memory bits, and we'll set them aside at some point during the program development, and switch to a global variable. So, memory bit, what does memory bit actually mean? At this point, we should actually write memory bit M0.0. For example, we could take any memory bit. We have thousands of them. And you just have to know that you can create a double assignment if you do not understand how memory bits work. And in this video, I would like to briefly demonstrate this overlap so that one understands why I personally try to avoid memory bits. So it is really fast, or rather, the access to the memory bits is relatively quick. They exist, they are fixed addressed, and I can just get started. M0.0, I have stored my state there and can continue programming. Creating a variable is a bit more cumbersome, and that's why most try to avoid it or this function. However, if you know what you can do with it, or rather what you can do wrong with such a memory bit, then you might reconsider your preferences, so to speak. I don't want to speak ill of the memory bit. It has a tradition. It originally had the essential function of using each individual bit in a memory byte, in a manner of speaking, or that you can use each individual bit in a memory byte. And that happened earlier, as mentioned, for memory-related reasons. Nowadays, you don't need that anymore because we have enough memory. And yes, I will introduce you to a small component called move. The move component, by the way, you can enter something up here that you might know by name, then the corresponding component is selected and highlighted in the list using the search function, or there is the second function or option. You take a black box and simply write move in here, press enter, or double enter, and then I also have the move block. And yes, how does this move block work? The move block has an enabled input. When it is assigned a variable, the number that is here will be passed to the variable that is there. I could simply write a constant here or use a variable. In this case, I would like to write a constant, so just a fixed number. That will be a 62, for instance, for example. And now I will simply write a marker at 0, okay? The marker at 0 should somehow get a 62. And if I don't predefine any variables or an input at this point, for example, it doesn't necessarily have to be a variable, then this function block will be executed permanently. This means that the 62 is permanently written to MB. 0. Let's take a quick look at the function after I've done it this way. This means I only need to transfer the male 1, and I will do that at this point as well. We observe the process and see that the 62 is in MB. 0. All good. Now we want to activate this function again. So I want to execute the SR through 0.0. I will do that now and find that somehow it no longer works. This will be reset immediately. Now the question arises, why is that? Let's take a look at the forest table. And in the forest table, I have now called MB0. I can represent marker 0.0 as a single bit. Here, we switch to observation mode and can see what happens. So, MB0, represented in binary, has a total of 8 bits. And we see on the right side, here on the right side is actually marker 0.0. And here is marker 0.7. So 0.0, 0.1, 0.2, 0.3, 4, 5, 6, and 7. And the number 64 consists of, which means in binary 1.1, 1.1, 1.0. When you convert it, you get from decimal 64 to binary 1.1, 1.1, 1.0. So, what happens? When we observe this, when I activate I 0.0, absolutely nothing because, and this is important, our PLC runs cyclically. That means we jump into the program block folder here, then main OB1, and edit the program from top to bottom. And here we said that M0.0 should be set. We will store that information. And in the next network, we say that a 62 should be written to MB0. This means we have double allocated the memory area of M0.0. We overwrite the individual bit, the fixed address bit M0.0, with the number 62, which inevitably places a 0 where 0.0 actually wants to be 1, as I just showed in the observation table. So what happens if we simply swap the two networks? So we can swap them, we have a different order, and upload the program to the PLC again. With the right mouse button, we can display the block or the variable as a decimal representation. And try to start the process again, namely this process. It went on briefly and then turned off again. Yes, so what happens? We will take another look at the whole thing in the process table. We are still in observation mode. Let's take a look at the whole thing. Do you see that? I not only couldn't start the process, but I also changed the number at the same time. It is no longer a 62 but a 63 because the first one is added and it has a value of 1. That means I have changed my quantity, whatever it may be, at this point. If you build it differently, now I will make another change. We go back to the main OB1 and simply set an input, I 0.2, so that we only start this process when we want to. That means it will not be executed permanently, but will be started when I activate this input. We will transfer the whole thing. Then it is such that by pressing this button here, I write the button, which is 62, into memory MB0. And if I now start my process, and now you can actually see that, because it is no longer overwritten by the 62, there is a 63 in there, and my process works. This means that if we are unlucky, we could distort the memory area not just by 1, but perhaps by a larger number. Again, to make the whole thing perhaps more understandable, I switch back to the forest table, and we now have the 1, 2, 4, 8, 16, 32, 64, 128. The 128, the value of an integer in a byte, also corresponds to the highest marker in this byte, which would be the 0.7. This means that if I were to make the mistake of using an M0.7 for this SR block instead of 0.0, which is already a mistake, I would not only distort my value by 1 unit or by 1, but I would distort it by a whole 128. Let's take a look at that now. So we are now writing a 62 in marker work 0 and activating a 0.7 to start the motor, for example. And behold, we have minus 66. This means that the first bits in a byte, seen from the left, are also reserved for a sign. So 0 means in the positive direction. 1 means in the negative direction. So I have distorted the value to such an extent that it has nothing to do with the original value anymore. We could try the whole thing with another bit, for example m0.6 instead of m0.7. We transfer the whole thing and overwrite the value again, and instead of 62, we have 126 there. This means we have added another 64, and our value now looks like this when we look at it in the observation table. Let me do that again. Top, reset. I do that again. So there is my 62 in it. And now I overwrite the value and suddenly got another 1 at this point. Just so you understand that. How can you work around this? Yes, of course, you can be careful that this doesn't happen, that you don't create any double assignments of any memory bytes. By simply saying, okay, if I'm already using them, then I should take a look at the tools in between and call up the allocation plan. And you can see that, here you can immediately see that I have used the entire byte and also the individual bit within that byte. And this is an error. That must not happen. You must not do that. And here all the markers are listed that I have used at some point during the programming phase. Here you can actually recognize this double allocation at first glance and eliminate it accordingly. The second option is you simply create a global data block. Name it, for example, GVL for global variable list, and confirm everything. And we have here a data tank of a global nature, just like the markers, where you can simply say, I need, for example, quantity, and of course of the data type integer. And then I have my quantity with the initial value of 0 of data type integer, and this is dependent on the name. There is no fixed address. The same applies to a Boolean variable, for example, SR block. I can call it SR01. I can declare it as a Boolean value. It only exists once. I can set it twice, but there is no overlap. Double allocation or overlap, as I just showed. At this point, I would say, let's make a cut. And in the next video, we will continue with the structuring and building of a program in TierPortal. Until then, I wish you a nice day, and say goodbye at this point. See you then. Bye.